Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at probability modeling. So calculus is very useful in probability modeling, particularly concerning continuous probability distributions. So what makes data continuous? Basically, it's measured. It can take any value within a range. An example would be if I looked at the height of a randomly selected person from our class. So the height's going to be between, say, like 160 and 185 centimeters, but really it can take any value within that range. Could be 163.2 or 168.9735 and so on. So that's what makes it continuous. So continuous probability distributions have a PDF or probability density function. It's from that function we can calculate probabilities. So there are two conditions for a valid PDF. The area under the curve has to be 1 and it can't assume negative values. Really, these two conditions need only hold over the interval for the values that x, the random variable, can take. Now the CDF is the integral of the PDF, and that will allow us to calculate some probabilities. So let's look at an example. So I want this function here to be a valid PDF. So let's find the value of k that makes it a valid PDF. In particular, I need to find the value of k so the area under this curve for x is greater than 1 is equal to 1. So I want the integral of k over x to the power of 5 with respect to x to equal 1. Now I'm actually integrating for x is greater than 1, so between 1 and infinity. Now because k is not the variable here, it's a constant, I can just take it out the front. Now when we're integrating 1 over x to the power of 5, you might find it easier to write that as x to the power of negative 5. So when we integrate, I'm going to leave the k there, we increase the power by 1 and divide by the new power. And I need to evaluate that between 1 and infinity. So again, I might make it easier on myself by rewriting this. X to the power of negative 4 over negative 4 can just be written as negative 1 over 4x to the power of 4. So now let's substitute in the value. So here I have to substitute infinity. Really what I'm finding is the limit of this function as x approaches infinity. Now if you have negative 1 divided by infinity, it actually gets closer and closer to 0. As x gets larger and larger, it approaches infinity. This will approach 0. So then I need to minus the function evaluated at 1. So at 1, it'll be negative 1 over 4. So what I have is k times 0 subtract negative a quarter equals 1. Solving that equation actually just gives me that k equals 4. So k equals 4 will make this a valid PDF because the area under the curve will be 1, and this will never assume negative values because x is positive. So if top and bottom are positive, then the function's always going to be positive. All right, let's now calculate the CDF. So the CDF is the integral from the lowest value x can take, in this case 1, up to x of the PDF. So we sort of did some of this work already. Because k is 4, we can seriously just substitute 4 in here. They will cancel out, and we get negative 1 on x to the power of 4, evaluated between 1 and x. So if you evaluate this at x, it just stays the same thing. So it'll be negative 1 on x to the power of 4, and then you subtract when x is 1, you get negative 1 over 1. We can just simplify this as 1 minus 1 over x to the power of 4. This here is our CDF, and that tells you the probability x is less than or equal to a certain value. So for example, if I want to find the probability that x is less than 2, note it doesn't matter whether you use less than 2 or less than or equal to, because in any continuous probability distribution, the probability of attaining a specific value is 0. The probability x is less than 2, all I do is substitute 2 into this formula here. I get 1 minus 1 over 16, which is 15 over 16. So that's how we can actually calculate probabilities. But when we have probability distributions, we're usually interested in the median, mean, mode, and standard deviation, so I'll calculate all of those. So as for the median, note we have our PDF, which is actually like this. So that's what it'll look like for this particular function, but not all functions. Now there will be a point along here such that the area is split into two equal parts, 0.5 and 0.5. Remember, to be a valid PDF, the entire area under the curve is 1, so the median is the x value, where the area is 0.5 to the left and 0.5 to the right. So because the CDF is the integral of the PDF, or the area under the PDF, then we can just find the median by finding where the CDF equals 0.5. So the CDF here was 1 minus 1 over x to the power of 4. So we just want that to be 0.5. So if I solve this equation, I just get 1 over x to the power of 4 equals a half. So since the numerators are equal, the denominators are equal. So in this case, x would have to be the fourth root of 2. So that number there will be the median. Let's now calculate the mean. So to calculate the mean, the idea is we have our curve here. We're taking each value, so each possible x value down here, multiplying it by the density and adding it up. Each x value, multiplying it by the density, adding up. Each x value, multiplying it by the density and adding up. And that's how we get the formula. We multiply each x value by its density and add them all up. That's precisely what integration is. So here px refers to the PDF. So we found out on the previous slide that the PDF was 4 over x to the power of 5. So for the mean, we just go x times PDF, and we need to integrate it over all the values that x can take. In this case, it was 1 to infinity. So really, we're integrating from 1 to infinity 4 over x to the power of 4. Once again, to integrate this, it might be a little easier to write this as 4x to the power of negative 4. So what we do is we leave the 4 for now, we increase the power by 1 and divide by the new power. And again, to make life easier on ourselves, we might rewrite that as negative 4 over 3x cubed. Now we're going to go ahead and evaluate that between 1 and infinity. So once again, substituting infinity makes this equal to 0. As x gets larger and larger, 4 divided by that just becomes smaller and smaller. It becomes 0. So we have 0 when x equals infinity. Now when x equals 1, it just becomes negative 4 on 3. The mean is 4 over 3. All right, let's now go ahead and calculate the standard deviation. So this is the formula for the standard deviation. Note that it involves the mean. So we first need to calculate this here. So this is the expected value of x squared. This time we're integrating x squared times the PDF, which was 4 over x to the power of 5. So once again, we're going to integrate it over all the values that x can take. So, of course, this is the same as just integrating 4 over x cubed, and we might find it easier to write that as 4 times x to the power of negative 3. So to integrate that, we increase the power by 1, divide by the new power. We're going to evaluate that at infinity and 1. So again, it'll probably be easier if we write this as, so 4 divided negative 2 is negative 2, and we put the x on the bottom. That helps us see much more clearly that when x is infinity, this will again be 0. When x equals 1, we get negative 2 over 1, which is negative 2. So this comes out to be 0, subtract negative 2, which is 2. So what we have here, the variance is going to be the integral we just found, which was 2, minus the mean squared. So that's what I mean by mu squared. So we actually get 2 over 9 for all of this stuff in the square root. So the standard deviation is just going to be the square root of 2 over 9. That's the exact value. All right, let's now calculate the mode. So you might be thinking to yourself, how can there be a mode when it's a continuous distribution? Because the probability x takes a specific value is always 0. But when we're looking for the mode, we're looking for the number around which the density is the greatest. So we're going to look again at our PDF, which was 4 over x to the power of 5. Now, if we want to find a local minimum or maximum, we know we can just differentiate this. So again, this is 4x to the minus 5. So if I want to differentiate this, I get negative 20x to the minus 4. The problem is that this can never equal 0. You can't have 0 to the power of something negative. So how then do we find the maximum or minimum value of the function? Well, the thing is here, we're only looking for the minimum or maximum in a given range. See, we're only looking at the function from x equals 1 up to x equals infinity. I know you can't actually draw infinity, but I just put it here to illustrate it. So it turns out if you have a function on a given interval, its maximum or minimum value will either occur at a stationary point or one of the endpoints. So since this has no stationary points, we look at the endpoints. So if you substitute in 1 for x, you just get 4 over x to the power of 5, 4 over 1 to the power of 5, which is 4. And if you substitute infinity, you get 4 divided by a really large number, which approaches 0. So the graph doesn't actually hit 0, it just approaches 0 as x gets closer to infinity. So clearly, the highest density occurred at x equals 1, and so x equals 1 is the mode. Now, I just want to point out something. It is true, probabilities can never be more than 1, yet our density function can be more than 1, because our density function doesn't tell us the probability. The probability x equals 1 is actually 0. That's why the density function doesn't really tell us the probability. But when we're finding the mode, what we're saying is that around 1 is the area of most likelihood to occur. Alright, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.